This is the second build in this series, and it starts the same place the first one did, on the Hugging Face model page before a single line of product code exists. Last time the job was captioning. This time it's object detection, not what is happening in this image, but what is in this frame and exactly where. The model is RT-DETR, Real-Time Detection Transformer, out of Peking University, Apache 2.0 licensed. Its pitch: the first real-time, end-to-end detector that doesn't need non-max suppression to clean up its own output. A hybrid encoder fuses features across scales, and the decoder picks its final boxes through learned query selection instead of a handwritten cleanup rule. It ships in sizes, small and fast, or bigger and more accurate. No lingering on the model page straight into a ChatGPT project mid-thought. We are exploring a new object detection model. Not what can this model do as an abstract question. Not yet. First comes the harder one. What would a real product built on it actually look like? Before landing on any specific use case, the conversation does something that's easy to skip in hindsight but matters a lot in practice. It sketches the shape of a generic video understanding product first, independent of what it'll actually be used for. An object table, frame, timestamp, class, confidence, bounding box, area percentage, zone, track ID. A timeline layer on top of it, person count over time, vehicle count over time, object appearance and disappearance, p-crowd frames. A zone editor where a user draws regions directly on the frame, entrance, counter, aisle, restricted area, and the app computes objects inside a zone, time spent in a zone, zone occupancy, zone crossing events. None of that names a use case yet. It's the generic skeleton any detection-based video product needs, sketched before committing to what it's for. And it's also exactly where the model's real boundaries get written down early. No identity recognition, no face recognition, no OCR, no intent detection. A box, a label, a confidence score. The product only gets to claim what the model can actually back up. Only after that generic skeleton exists does the conversation compare specific directions to hang it on. Four get ranked side by side: CCTV and security scene auditing, retail and shop floor analytics, traffic and parking monitoring, personal video search for object moments. Traffic and parking needed vehicle-specific tuning the base model doesn't ship with. Personal video search ran straight into the model's limited vocabulary. No captions, no identity, no rich semantic search, likely to disappoint. CCTV and shop floor audit ranked highest for the same reason. Fixed camera, known entry points, a small vocabulary of things actually worth watching, narrow enough to finish, real enough to matter. With CCTV chosen, the same zone and rule skeleton from the generic brainstorm comes back, except now it's concrete instead of abstract. A short product flow. Choose the product surface, define zones on a real frame, attach rules to those zones, review what the rules catch. Zone types stop being placeholders and become specific. Entry line, aisle, restricted edge, waiting lane. This is the same idea as before, but this time it's the idea the product actually ships with. Before committing fully, one more real decision gets made out loud. Shop and store or warehouse. Warehouse is the more product-interesting direction. Truck loading bays, weighbridges, pallets, but harder to source realistic free footage for. Shop and store is easier to start with data that actually exists, so the search happens right there, live, querying Hugging Face for CCTV and warehouse surveillance-style datasets. No clean warehouse dataset turns up, related demo spaces, nothing that fits. Shop and store wins, and not just on product merit. It wins because it's the direction with footage you can actually get your hands on. A product decision with the direction locked, the spec gets specific fast. Clip type, zones, rules, output, each with its own filled-in table now, not a placeholder. This is where the audit trail decision gets made explicit. Every claim the product makes has to trace back to a specific frame and a specific detection. Evidence first language, always, person entered restricted zone, never suspicious activity detected. A detection model has no business claiming it understood intent. Then the conversation turns into a handoff document. A design guide and mock-up get generated, a dashboard, a zones editor, an event timeline, a reports panel sketched before a line of code exists. And the actual written spec gets saved to disk as a markdown file, grounded in the real RT-DETR model constraints and real CAVIAR video availability. The summary decision, spelled out plainly: build the first ScenePulse Watch surface around shop and store CCTV audit using CAVIAR. The strongest initial jobs: count movement through entrances, watch shop counters and waiting areas for restricted zone violations, find review moments from object persistence. The core product differentiator, in one line: RT-DETR detects objects. ScenePulse decides what that means. That's the actual contract that gets handed off, not build an app, but a specific pipeline. Video in, detections, product tone tracking, zones, rules, events, evidence, audit report out. Spec file saved. Design mockup downloaded. One more saved dialog, a glance at the Finder window confirming both files landed, then the switch away from the browser entirely. Spec closed, codex opens. Everything from here is the build. What you're watching here is sped up roughly 10 times over, hours of an agent working compressed into minutes, because watching code get typed in real time isn't the interesting part of this build. What it actually produced is: first target, get off fake data. Builds like this tend to start with a dashboard full of plausible-looking numbers that don't come from anywhere real, a KPI strip that looks convincing in a screenshot and means nothing underneath. That gets ripped out first. The workspace gets wired to load real, persisted analysis artifacts, and the live path runs actual RT-DETR inference instead of decorating a screen with sample values. That sounds like a small ordering choice. Do the real thing before the demo polish. But it's the difference between a product and a mock-up wearing a product's clothes. Every number an operator sees later has to trace back to a real run, or none of the rest of this matters. Worth actually pausing on what's running under the hood here, since this is the part of the stack that never changes no matter how the product evolves around it. The paper behind RT-DETR calls it the first real-time end-to-end object detector. And the end-to-end part is doing real work in that sentence. A YOLO family model predicts a big pile of overlapping candidate boxes for every object, then runs a separate non-max suppression pass afterward to throw out the duplicates and keep the best one. That extra pass is itself a hand-tuned algorithm with its own thresholds, its own edge cases, its own way of quietly failing on crowded scenes. RT-DETR removes it entirely, a design it inherits from the DETR transformer detector family more broadly, not something unique to RT-DETR itself. Two specific pieces make that removal actually work in practice, not just in theory. A hybrid encoder splits the usual all-at-once attention computation into two cheaper stages. Intrascale interaction first, so features at the same resolution talk to each other, then cross-scale fusion, so information moves between resolutions afterward, instead of one expensive combined pass. And on the decoder side, uncertainty minimal query selection handpicks the highest confidence starting guesses from the encoder to feed the decoder, rather than handing it a generic, uninformed set of queries and making it work harder to converge. Together, those two choices are most of the reason this architecture can skip NMS and still land clean, non-duplicated boxes. And it's not just fast next to YOLO, it's fast next to its own family too. Against Dino R50, which was the strongest prior transformer-based detector before this paper, RT-DETR R50 posts 2.2 more AP and roughly 21 times the frame rate. That's not an incremental win. That's the difference between transformer detectors are accurate but impractical for real-time video, and transformer detectors are now the practical choice. It also ships with flexible speed tuning. Swap how many decoder layers run at inference time, no retraining required, to trade a little accuracy for a lot of speed when a deployment actually needs it. That flexibility is exactly why a small-end fast variant and a large-end accurate variant of the same underlying model both exist for this build to choose between later. Next, the product can't stay tied to one bundled demo dataset forever, so upload support goes in early rather than as an afterthought. The API accepts a real video, stores it under its own upload ID, generates a browser-playable preview, and this is the important part, runs it through the exact same analysis pipeline as the bundled CAVIAR samples. No separate demo path and real path quietly diverging over time. One pipeline, two sources of video. That's a structural decision that pays off months later when the bundled samples stop being the point and real footage is. Then the review surface itself gets rebuilt around evidence instead of decoration. The video player and the timeline scrubber move to the top of the page, because in a review tool, time control is the primary job, not a KPI strip sitting above a video that's really an afterthought underneath it. Selecting an event or a frame now drives the video, the overlays, and the detail panel together, as one connected surface instead of three components that happen to share a page. And underneath all of that, every sampled frame with a detection on it gets persisted and made searchable by timestamp, by object label, by the actual wording of the event. That's the difference between the model found something and the operator can go find it again. A detection that can't be retrieved later isn't evidence. It's a log line nobody will ever read. This build treats that retrieval path as core, not a stretch goal. Runtime honesty gets built in at the same time, not bolted on later. Every analysis now persists what device it ran on, whether it was a warm or cold start, how long the model took to load versus how long inference actually took, and which classes and labels were configured for that run. That's the difference between a product that can explain why a run felt slow and one that just shrugs at you. If cold start on this machine takes 11 seconds and warm inference takes half a second, the product should be able to say so, not leave the operator guessing whether something's broken. A good chunk of this stretch is codex testing, what it just built, running the pipeline against the CAVIAR sample clips, checking that detections land where they should, catching cases where the review surface claimed something the underlying data didn't actually support. Worth explaining what CAVIAR actually is, since it's doing a lot of quiet work in this build and it's easy to just call it the sample dataset and move on. CAVIAR Context-Aware Vision using Image-Based Active Recognition is a fixed camera surveillance dataset from 2 real sites, an entrance lobby at INRIA Labs and a shopping center hallway in Lisbon. The footage is old by modern standards, half-resolution PAL, 384 by 288, 25 frames a second compressed as MPEG-2, most individual clips only 6 to 21 megabytes. But the content is exactly the shape this product needs. Acted scenarios of people walking past a shop, entering and exiting, waiting near an entrance, leaving a bag behind. Clips named things like walk by shop 1 core, enter-exit crossing paths, 1 leave shop, left bag at chair, left bag picked up. Literally the CCTV vocabulary the product Spec was built around, pre-labeled and licensed Creative Commons BYSA for exactly this kind of reuse. Old dataset, right shape. That combination is worth more here than a newer, higher resolution dataset that doesn't match the actual use case. One real engineering pivot worth calling out here in actual numbers, not just bigger versus smaller, because it's a genuine product management lesson and not a footnote. The spec was written around RT-DETR R50VD COCO 0365, 42 million parameters, pre-trained on objects 365 before COCO 55.3 AP, 108 frames a second on the paper's own benchmark hardware. The strongest accuracy the RT-DETR family ships. What actually shipped as the live default is RT-DETR R18VD, 20 million parameters, 46.5 AP, 217 frames a second. Almost 9 points of accuracy given up. Roughly double the frame rate gain back. That's not a mistake, and it's not a failure to follow the plan. On paper, the bigger model is strictly better, more accurate, full stop. But this product runs locally, on a laptop, without a dedicated GPU queue sitting behind every request, and every one of those 108 versus 217 frames has to actually get processed on that machine. A model that scores 9 points higher in a benchmark table and makes the live review workspace feel sluggish isn't the better product decision. It's a worse one wearing a better spec sheet. The spec is a hypothesis written before anyone felt the runtime. Reality met it, and reality won. The actual mistake would have been shipping the bigger model anyway just to match the document, and letting the product feel slow so the spec could stay correct on paper. That same instinct, trust the runtime over the assumption, shows up repeatedly through this stretch, not just once. Apple Silicon acceleration gets tried because it should, in principle, be faster than plain CPU. But the current RT-DETR path hits an unsupported floating point operation on the GPU backend. Rather than silently eating that failure, the app falls back to CPU and records that it did, so a slow run reads as, here's what actually happened and why. Not as an unexplained mystery the operator has to debug themselves later. There's a benchmarking lane opened here too, and it's worth narrating precisely because of what it deliberately does not do yet. An ONNX runtime path gets explored as a possible CPU speedup, and an MLX path gets floated as an Apple native option, and both get parked, on the record, as research rather than adopted, not because they're bad ideas. Because there's no verified, parity-checked path, yet that proves either one actually improves this specific workflow without quietly changing what the product outputs. That's a guardrail, not indecision. Don't hand ownership of the detection path to a second, unproven runtime just because it looks appealing in a benchmark thread. Adopt only with evidence in hand. Same posture shows up in what happens to unavailable data. Some of the reference clips in the CAVIAR manifest were never meant to be run locally. They're reference-only entries. Early on, requesting one of those directly could throw an unhandled server error, which reads to an operator like, "This app is broken." That gets fixed to return a clear conflict response instead, and the UI disables those samples up front. An unavailable source should read like a data availability question, not like the whole inference pipeline just crashed. Small fix, same underlying discipline as everything else in this stretch. Never let the product imply more confidence or hide more uncertainty than the evidence actually supports. Somewhere around here, the product stops being a detector viewer and starts being the thing it was actually specs to be, back at the very start of this episode. Zones get drawn directly on the frame, created, selected, moved, resized, with exact numeric inputs still available underneath for anyone who wants precision over dragging a handle. That's the zone half of the original spec, made real and editable instead of living as a hard-coded default no operator could ever touch. On top of the zones, rule-driven events, which is really the whole point of this product. A person crossing into waiting lane, a count exceeding a configured threshold. And a detail that matters more than it looks like it should. Duplicate-looking detections happening in the same moment get grouped into one clear line, instead of surfacing as three near-identical alerts. Two people entered shop entrance, not three ambiguous rows that leave an operator wondering whether the system double-counted one person or genuinely saw two. That grouping logic is a small piece of UI wording with an outsized effect on whether a human reviewer actually trusts the tool enough to act on what it says. The review workflow itself gets reordered around the same principle. Time control belongs to the video surface. That's the primary job in a review tool. Evidence validation belongs to the extracted frame sitting right below it, with zone and detection overlays attached so it can be checked spatially, not just read as text. Live events stay bounded with their own internal scroll instead of stretching the whole page, because a workstation should feel like a workstation an operator returns to for hours, not an infinite document you scroll through once and never find anything in again. CAVIAR wasn't the only dataset in the running, and it's worth naming what else got looked at, because we picked the first thing we found, and we researched the landscape and picked the best fit for this stage, are very different claims to be able to make. MEVA was a real candidate, much heavier and much richer than CAVIAR, modern multi-camera surveillance footage, licensed CC by 40, and hosted on AWS S3 through the AWS Public Dataset Program. But richer also means heavier to work with, and it's a better fit for later validation once the pipeline is proven than for a first working demo. TinyVirat came up too, available straight off GitHub, but built around low-resolution action recognition rather than fixed camera CCTV scenes, which makes it useful for some things and a poor visual fit for a first ScenePulse showcase. Pexels and Pixabay filled in as supplementary clean stock footage once shop and store was chosen over warehouse. CAVIAR won this round not because it's the best dataset in the abstract, but because it's the best dataset for proving this specific product works, right now, on real acted footage that matches the zones and rules just described. This is the payoff of the evidence-first decision, made all the way back in the ChatGPT conversation that opened this episode. Every event links to a real extracted frame, not a generic icon standing in for something happened, the actual frame the detection fired on. The scrubber shows event markers and extracted frame markers on the same timeline, so an operator can move from "here's an alert" to "here's the exact frame that justifies it" in a single motion, not a support ticket. KPI cards up top aren't decorative either. They're derived directly from the loaded run rather than static summary prose. Each one explains its own metric in plain operator language, and clicking one jumps into the same event and frame selection the rest of the page already uses. One state, one source of truth, reachable from 3 different entry points on the page. That's what the model supplies detections. The product supplies meaning. Looks like once it's actually built instead of just written down in a spec document. Worth naming what's actually inside one of those detections, since every evidence frame you're looking at is built from the same fixed shape underneath. An ID, a source ID linking back to the exact clip, a frame index and timestamp, a label, a confidence score, a bounding box, and a box area ratio. How much of the frame that box actually covers? That last field earns its keep in ways that aren't obvious at first. A shrinking box area ratio on a tracked object across frames is a cheap, honest signal for this thing is walking away from the camera. A box that stays roughly the same size and position for a long stretch, with no matching person nearby anymore, is exactly the shape of a left-behind bag, without needing a model that understands left behind as a concept at all. And none of this runs on every single frame of source video either. Frames get sampled at a rate that trades thoroughness against compute cost, and that sampling rate is itself part of the runtime metadata this build already commits to recording. A fixed type detection shape is what lets a database index it, a UI render it consistently, and an export contain it, turning a raw model output into something the rest of the product can actually build on top of. The intended operator loop is visible here too, even where it isn't fully closed yet. Choose a source, run or load an analysis, inspect the evidence it produced, adjust zones, adjust rules, review the grouped alerts that come out, inspect the frames backing them, export an audit artifact at the end. Every piece of that loop you're watching get built and tested is aimed at that full cycle, not at any one screen in isolation. Worth being honest about what this build is and isn't on camera, because a product series that only shows finished features isn't actually teaching anything useful. Rule authoring from the UI isn't done. Zones are editable, but the rules watching those zones are still Bootstrap-derived defaults, not something an operator can write, enable, disable, or tune themselves yet. That's not a minor gap. Zone editing without real rule authoring is only half a product, because the operator still can't express what they actually want the system watching for in a given area. Uploaded video has no Bootstrap review profile of its own, so a fresh upload lands with real detections and no clear review intent attached to it. No starting zones, no starting rules, nothing telling the operator where to begin. And there's no clean, reevaluate rules against what we already detected path yet either. Editing a zone updates stored configuration, but rerunning event derivation from existing detections and tracks, without paying for inference all over again, isn't built. That matters more than it sounds like it should, because it's the actual bridge between a first analysis run and the iterative review loop this product is supposed to support. Related to that, review profiles themselves are still source-controlled defaults in the repo, not a persisted, operator-editable configuration layer. So today, changing what a profile watches for means editing a file, not using the app. None of that is a failure. It's a closure list written down on purpose so the next pass has an order instead of a vague sense of make it better. Rule editing and rerun from stored artifacts first. Upload Bootstrap profile selection next. Then KPI drill downs into full filtered event slices. So a KPI card stops being just a jump to one representative frame and starts being a real filter. The canonical shape of the product video in, detections, tracks, zones, rules, events, evidence, exports is real and working end to end already. What's left from here is depth, not direction. A few guardrails sit alongside that closure list, and they matter as much as the list itself. Don't add a second long-lived inference path without benchmark evidence and parity checks. Don't move tracking, zones, rules, or event semantics into an external dependency just because it's convenient. Don't let the interface imply a certainty the detection pipeline can't actually justify. Gaps get closed over time. Discipline about how they get closed is what keeps the product honest while that happens. Step back from the code for a second, because the actual lesson of this episode was never really in the bounding boxes. 1. The model is not the product. RT-DETR draws a box and a label, frame by frame, and nothing more. ScenePulse decides what that box means, when it's worth an operator's attention, and how to prove it to a human later with an actual frame instead of a confidence score. That gap between raw model output and usable product is where almost all the real engineering effort in this build went. And it's the exact gap we added AI to it, pitch tends to skip straight past. 2. A spec is a starting hypothesis, not a binding contract. The model swap from R50VD to R18VD wasn't a failure to follow the plan. It was the plan meeting a real runtime constraint and updating, on the record, instead of quietly pretending nothing had changed. The guardrail isn't never deviate from the spec. It's never deviate silently. 3. Evidence-first language is what keeps a detection product honest, and it's a discipline, not a slogan. Person entered restricted zone is something this pipeline can actually prove with a frame and a box. Suspicious activity detected is something it can never prove, and a product that says it anyway is borrowing trust from the operator that the underlying model never earned. The same discipline is why a second inference runtime doesn't get adopted without benchmark evidence in hand, and why an unavailable clip reads as a data problem instead of a broken app. None of that is polish. It's the actual product. That's the build. Same series, same local first, same-day philosophy as build memory, different model, different constraints, same underlying question. What does it actually take to turn a hugging face model page into something a real operator could use and trust? Next episode, a different model, and we do this again.